Log on, tune in, find out. Another good idea from Cambridge.
Angela Dean, and she's going to be talking on screening strategies in the presence of interactions, or maybe comparison of strategies here too.
Oh yes, I changed the first part of the title and I've forgotten I added a second part onto it. Well anyway, first of all I would like to thank Rosemary and Basher and the other organisers for inviting me to spend time here, and also Steve and Dave for inviting me to give this talk. This actually is joint work with Dave and Sue and Anna Vine and Danelle Dragulic. So we were interested in comparing a number of screening strategies, and I know many of you will know what screening is, but I'm going to put in a little short introduction just in case there's anybody who doesn't. So that's the first part. Then I'll talk about two different screening strategies that we've been interested in, and for a long time now some people have been doing group screening and some people have been doing supersaturated designs, and it became obvious that we needed to compare these strategies somehow. And then the question is, well, if you're going to compare the strategies, what kind of analysis are you going to do? And so I'll talk again about these later on, but we looked at 5 different methods of analysis. And then we did a simulation study to try to compare these methods. And if I've got time at the end, I'd like to talk a little bit about issues for simulations of this type. Okay, so screening then is the process of sifting through a very large number of potentially important factors. And what you're trying to do is to discover the few important factors. Now, what I don't mean is, well, first of all, what I do mean is if a factor is important or active, it has a substantial effect on the response average or the response variability through main effects or interactions. What it doesn't mean is it just has a non-zero effect. So we're looking for big effects, at least relatively big effects of a few factors. And the reason for this is that oftentimes you're doing screening when the engineers already have a prototype, and they're not going to change the prototype unless they get a big cost benefit from doing the change. So that means that we can assume factor sparsity. That means in our big pool of factors there are only a very few that have a large effect on the response. We are going to be taking relatively few observations relative to the number of effects that we want to estimate, with the idea that later on there'll be a follow-up experiment, and whatever we have discovered about active factors or active main effects or interactions will be investigated in more detail later, and then a detailed model will be fitted for prediction and optimization. So here we're only trying to find out which are the important effects. That means that, and Brad may disagree with me in a minute because he's going to talk about three level factors, but that means that we can get away often with doing experiments with factors at only 2 levels. And then we always get asked, well, supposing you expect a nonlinear response. Well, what we would try to do then is to ask the engineers where they anticipate this response might turn, and then we can take our 2 levels here at the steepest part of the curve, because ultimately all we want to know is this curve really steep, or is it just a flat kind of curve that we don't need to worry too much about? So here, very briefly, is an experiment that we did at Jaguar Cars. There's a nice picture that they gave us of a Jaguar engine. They wouldn't give us the car, they just gave us a picture. And now I'm getting that noise as well. It might be something to do with... No.
Someone's got their phone.
Has somebody got a phone switched on? No? No. Yeah, switch. Yes, if you have your phone on at all, could you switch it completely off, please? Okay, so the aim of this experiment was to find out which factors most affected the cold start performance of a new generation Jaguar engine. So as you can see, the prototype of the engine is already there, and they only want to change things if there's a large effect. They already knew about some factors that might affect the response. They'd already optimized some of the factors as much as they could, and they still weren't satisfied with the performance, and they wanted to improve it. So Sue and her colleagues set up a web-based tool which allowed engineers in three different countries to input the knowledge that they knew, and ultimately we ended up with a list of about 40 factors that they thought might possibly affect the cold start performance of the engine. Then what would be nice is if we had done a 40-factor screening experiment, but we didn't actually at that time. The factors were assessed, and some of them were combined into a single factor, some were held constant, some couldn't be held constant and had to be just allowed to fluctuate. So ultimately we had 10 factors left in the screening experiment, and we wanted to look at main effects, and in particular the two-factor interactions. Okay, the engineers already knew more about main effects than they did interactions. In fact, they knew very little about the interactions. So this is the goal of the kind of screening experiment that we're interested in, is to try to estimate the interactions up front. Now, a traditional approach, an old approach to screening, is run a small experiment, estimate only the main effects, select factors with the large main effects, and then use follow-up experimentation to investigate interactions amongst only those active main effects. And that was called strong effect heredity by Hamada and Wu. There are other strategies that have come along later which I don't have a time to talk about, but let me just say that this strategy would not have worked in this example, because we found that pretty much apart from temperature, there were really no main effects that were active at all, and it was the interactions that were playing the main role. And here's one of the many, many pictures. If you think about the main effect, it's here somewhere, and the slope of that line, it's not zero, but it's small compared with the size of the interaction, and it doesn't turn up whatever method you want to analyze the experiment in, which means that cranking fuel would have been screened out at stage one, and you would never have got to investigate the interaction, this important interaction, at stage two. So with that in mind, we wanted to look at screening strategies in which you measure the interactions at stage one. There are a couple of recent papers stressing the importance of screening interactions. Bob Wilkinson, Dennis Lin are both here, and I think and Wenqi Wang is here. Okay, so these were the two strategies that we wanted to investigate. And when I gave a talk at the ASA local chapter in Cleveland some years ago, there were two different distinct groups of people there, and the people from the medical areas all came up to me afterwards and said, oh, we do group screening all the time. I wouldn't want to do supersaturated designs because the estimates are correlated. And the people in industry came up and said, oh, we like doing supersaturated designs. We wouldn't want to do group screening because estimates effects are aliased. So it was kind of interesting, and so they said, well, which is the best strategy? And I said at that time, well, I don't know. So here's our attempt to answer that. So first of all, for those of you who don't know, this is what group screening is. Here's an example with 10 factors, and I put them into groups. Here are groups of size 2, but the groups don't have to be the same size. They can be any size you like. In stage 1, we're going to perform an experiment on the grouped factors, which means that if I decide that group factor G1 is at the high level, what I really mean is that the two factors within the group are both at the high level. And if G1 is at a low level, then both of the factors within the group are at the low level. And I pick out the important or the active groups, and then I'm going to dismantle those and do a further experiment on the individual factors within those groups, holding everything else at a nominal level. Okay, so here's the procedure again in a little more detail. With the group factors, we're going to estimate the main effects and the interactions between those grouped factors. We're going to pick out the ones with the large effects, and we've got to talk about the analysis method in a minute. We declare those group factors to be active. And then if a group factor was inactive, then those individual factors will be held at nominal levels at stage 2. If the group factor was active, we'll measure the main effects of all the individual factors in that group and the two-factor interactions among the factors in that group. And if at stage 1, 2 grouped factors were involved in an active interaction, and I'm only talking about two-factor interactions in this talk, then we'll measure the interactions between the individual factors in the different groups. Okay, so here's what the worry is from some people, that you are aliasing main effects and two-factor interactions by doing this grouping. So this is the grouping that I just did with A, B in the same group, C, D in the same group. So at stage 1, I cannot estimate the interaction A, B, or C, D, or E, F, etc. There's aliasing induced between the main effects, and there's aliasing induced by the interactions between the group effects. Okay, now if you look very carefully at these interaction chains here, what you find is that within the chain, you've only ever got interactions between factors in 2 groups. And this is true even if you've got hundreds of factors, and doesn't matter how big the group size is. So the good thing about that is that if you really have a factor sparsity and there's not very much going on here, and you're just trying to find a few active effects, you're going to be able to throw out strings of factors, and at stage 2 you're going to be able to do a very small experiment. For those of you who don't know what supersaturated designs are, I haven't actually put up an example. I think several other people have talked about supersaturated designs already, but in these you have fewer runs than effects to be estimated. Nothing is completely aliased. In fact, some main effects and interactions are actually independent of each other, but others are correlated. And if you look through the papers, you keep seeing this number of third pop up, and typically the results that I've seen say that a good supersaturated design is one in which the design columns have correlations less than or equal to a third. There are many different construction methods in the literature. There's also an algorithm of Brad Jones, Dennis Lin, and Chris Knoxheim, which will find the best d-optimal, oh, I've left out Bayesian, I'm sorry, to find the best Bayesian d-optimal supersaturated design for estimating a given set of factorial effects. Now we're going to make use of this algorithm because in a simulation setting where you want to run around the loop 1,000 times, you want to be able to generate designs. You can't go into the literature and pull out good constructed designs. Okay, analysis. There's been a lot of different papers comparing analysis methods, and they haven't been very all-encompassing simulation studies. They've tended to be fairly small studies that I have seen. So we picked up what appeared to be some of the best methods from those papers to investigate them further. So there's the SCAD method, which was introduced by Dennis Lin and co-authors. The lasso is probably well known, Danzig selector, and then a couple of Bayesian methods, Bayesian model selection and a Bayesian model averaging with maximum a posteriori estimation. And I don't have time to go into any of those to say what they are. Then with this two-stage group screening, we threw in a standard kind of method using R squared, where we added terms into the model until the R squared hit a ceiling. We used the Danzig selector, and we used the 2 Bayesian methods. So altogether we're going to look at these 2 different designs, and 5 methods for that one and 4 methods for this one. Just to say briefly in passing that SCAD, lasso, and Danzig selector are all penalized regression methods, and they all have tuning parameters. And the choice of tuning parameters is critical in how well the procedures perform. And we did spend quite a lot of time trying to tune these procedures. We used a modified AIC criterion for lasso and Danzig selector, and for SCAD we used a generalized cross-validation. And the Bayesian methods too, before I get to that, we also threw in a threshold, because again, we're not looking for non-zero effects, we're looking for sizable effects. And so the engineers will tell you, I'm not interested in any effect that's smaller than so much. So we actually put in a threshold as well, which we linked to the size of our effects to screen out the small effects. The Bayesian analysis methods then were, you can select the union of effects in models with high posterior probability, select effects whose regression coefficients have maximum a posteriori estimates, and again, I'm sorry I don't have time to talk about what all these are. But again, they do have tuning parameters, and Dave in particular has spent a long time trying to tune the parameters in the prior distributions to get the methods to work as well as possible. And another piece of work that we did was to develop prior distributions at stage 2 of group screening based on the posterior distributions at stage 1. And if you're interested in the paper that has all these details, I will gladly give you the information afterwards. Okay, so simulation study. How do you compare all these different methods and these different designs? Well, first of all, you have to pick the number of factors, and we picked 10, 15, or 20, and we deliberately made them a multiple of 5 because somehow we wanted to use the same fractional factorial at stage 1 of group screening, no matter how many factors we had. So that means if you've got 10 factors, the groups are of size 2. If you've got 15 factors, the groups are of size 3, and so on. Now, we don't know what's going to happen at stage 1. We generate the data, we do one of these analysis methods, and some number of factors turn out to be important. So we need a design for stage 2. So we couldn't take a fraction, we had to do something that we could just bury into the simulation. So we took Jones-Lin and Narsheim algorithm that generated supersaturated designs and adapted it to generate designs with the number of runs equal to the number of effects to be estimated plus 5. So this is not a supersaturated design. This still has plenty of degrees of freedom. For the supersaturated designs, then we used Jones-Lin and Narsheim algorithm, and I'm skipping what Bayesian parameters we used in that. Now, what size supersaturated design should we use in a simulation? Because we don't know what's going to happen at group screening. So we have a choice. Either you run the groups, generate one set of data, run the group screening, see how many observations you used, then generate a supersaturated design of exactly that same size and see how well the two do. We decided not to do that because in practice, if you're trying to choose between these two strategies, you wouldn't be able to match up one run of a group screening design with one supersaturated design. But you can go to a website, which again I can give you information on later, which will tell you what the expected size of a group screening design is for given parameter sizes, and therefore you can pick, if you wanted to, or you could see whether the supersaturated design that you were thinking of using was that same size, smaller or bigger. So in the simulation then, we're going to run the group screening multiple times, find out the average size, the median size, and then we'll compare that with the supersaturated design of that same medium size. Okay, so what we end up with is for 10 factors with plus the interactions, that's 56 effects, including the mean that you're trying to estimate. We're looking in our simulation of 32 runs. For 15 factors, 121 effects, we're looking at 58 runs, and 20 factors, 211 effects, we're looking at 94 runs. We could have chosen different sizes, but that's what we chose. Okay, now which main effects are active? Sometimes in the literature you will see a supersaturated design and the authors will say, well, let's suppose that factors 1, 15, 19 are active. We didn't want to do that. So we took each main effect and each one had a certain probability of being active. So on one run of the simulation, every main effect may have had a probability 0.05 of being active. On another run of the simulation, we picked a different number, and so on. Then we use the conditional probability in, I think it's Chipman, Hamada, and Wu paper for assessing a probability of an interaction being active. And then if the effect is active, we generated on one run of the simulation from this size, another run from this size, another run from this distribution here. Inactive effects we generated from either this or this, and then we took the size, we took the sign of the effect. For the inactive ones, we took the sign to be plus or minus with probability of half. The active effects, if they were main effects, we kept the sign to be positive. If they were interactions, we took the sign to be plus or minus with probability of half. Okay, and then given we now have the effects, which ones are active, what the effect sizes are, we have the design that gives us the X, the model, and we generate the random error from a distribution. And then we analyze the data using each of the methods, and we did this 1,000 times for every possible combination of those settings. And here's, before that, we had to then compare the methods, and we selected the following 4 set measures of goodness: sensitivity, proportion of active effects, which actually got detected; type 1 error, the proportion of inactive effects that we actually said mistakenly were active; false discovery rate, how many of the active effects, or how many of the effects that we said were active were actually inactive; and then we compared the size of the model, the true size of the model, with the model size that we said that we declared. And here's an example of one picture, and you probably can't see it way at the back, and I apologize for the 3b.pdf at the bottom, which I couldn't get rid of. Okay, so this is active, 0.2 of the main effects being active. They're drawn from this distribution here. The interactions are drawn from the same distribution for those that are active. All the inactive effects are drawn from this distribution here. And then we had no idea what was going to happen. And this is just one more or less typical picture. In some settings, all the methods do well, so that wouldn't have been too interesting to show you. This is a difficult setting because the inactive distribution is so spread out. And what we see, and actually I was quite surprised, I don't know about the others, but this is the group screening using the Danzig selector. It has very high sensitivity. It has very low type 1 error. It has very low false discovery rate, and that means therefore that the model size must be about right. So group screening with the Danzig selector does seem to be a viable possibility. It did perform well. Of the supersaturated design, of the 3 methods we looked at on this picture, all of them have reasonable sensitivity, but the SCAD tended to have, and in all the settings we looked at, SCAD tended to have high false discovery rate. Of the Bayesian methods, type 1 error is great, the false discovery rate is great, but what we couldn't get to work too well was to get the sensitivity high, so there's more work to be done there. Okay, so I think Sue's going to stop me soon, but so let me just give a summary of this. The Danzig selector with group screening seems to perform the best overall if you look over all the settings and all the thousands of box plots that we actually produced, followed by the lasso and the Danzig selector in the supersaturated design. The SCAD in the supersaturated design tended to have high false discovery rate, and just using R² with the group screening resulted in low sensitivity, so that wasn't so good either. The Bayesian model selection in the supersaturated design sometimes had a very high type 1 error rate, and the Bayesian methods tended to have a greater drop in performance when you got to some of the difficult cases to identify than the frequentist methods did. So I think I've talked about some of the issues of simulations as I've gone through, so if I stop here we can take questions.
I enjoyed the paper. On the Bayesian, if I understood it right, that you did a union of the high probability models and did a union of the terms for the one, and then the other was a maximum story, right? So the other one was like picking the best model?
I'm going to throw this question over to my co-author.
So yeah, the first method is picking the models, a subset of models with high posterior probability. Second method is looking at a model average estimate of the regression coefficients, and then picking the largest model average, effects the largest model average coefficients.
Okay, so I guess in the first one you'd expect maybe a high type 1 error, right? Because I would normally, I always go towards sort of the marginal probabilities, and the marginal probabilities you could have at the highest, the best model could actually, its terms may not be the ones that it would pick, right? So, but the second approach isn't quite marginal either, right? It's closer, I guess, right?
It's trying to mimic what we were doing with the frequentist methods, looking at regression coefficients rather than model
Okay.
You mentioned two design options, supersaturated and grouped screening.
Yes.
And I just wanted to bring forward a third possible option for this case. That's using orthogonal arrays of strength 3, which are in fact supersaturated for the interaction effects.
You mean you're fitting the main effects and the interactions at the same time?
They don't allow for all of these, but you are permitted to search for interactions, and these are orthogonal to the main effects.
Okay, so they're search designs, and you can search for up to some given number of interactions. Right. Okay, yes, that's another possibility in which we didn't put into that. That's right. Yeah, thanks.
You know, it's already an enormous simulation, and probably most of the questioners will add other things.
Yes, probably.
I feel the comparison's a bit unfair to supersaturated designs, because I'd be interested to see a more heavily supersaturated design with a small follow-up, which seems to me would be a much better strategy.
That's
than
another.
most.
Yeah, that's another possibility. Take a smaller supersaturated design, analyze that, and then take what look like the active effects from that, do a smaller follow-up design, and then analyze that. Yeah, that's a good idea too. Yeah. Okay, we got two more.
When you say that design is super saturated, I get it from reading that because you count also the interactions, right?
Yes.
In the simulation, okay, good. So if you only count the main effects, then the design are not super saturated.
That's probably true.
Okay, so
Yeah. Well,
then actually you refer to the Hamada-Wu strategy. That one would do that as an alternative. You don't need you start with a design with complex areas in like 20, 24, whatever, for the 2 level. And then that is actually super saturated once you consider interaction. And our strategy actually is not 2 stages. You refer to it's 1 stage. It just, you can do interaction and main effect by different models selection strategy.
Yes, I know, but in our case, we wouldn't have picked. I don't think we would have picked up the interactions, or maybe I'm Maybe
Well,
I'm
I don't know
playing
that, but
it,
that's because in our study, all the sample size very small.
yes.
But if I do yours, I'm not saying this is the
Yeah,
best,
yeah.
I'm saying this is an alternative.
Yes.
I can choose a very simple plaque-Berman design or maybe 36 run or 40 run.
Yeah.
So that's one. Second one is the pair with Xiaowei Chen and Wu in Silica 2000. They will extend the idea to be able to estimate curvature. So now I start with a non-regular 3-level design, like 36 and others. So the same idea. And now it's again one experiment. We can analyze in 2 stages. Another 2 stages is one design. So for example, you would do interaction, do screening, and collapse, and then on the remaining one you can do interaction. Of course, this may have some pitfall because when you do collapsing, you may also miss out something. But this, I
Yes,
thought this may
yeah.
be something that you can consider.
No, I know that paper, and we did consider all of these things, but it seemed to us that, especially in this particular experiment where no main effects turned out to be active, all the action was in the interactions.
Then we
Yeah.
know.
Yeah.
Maybe just one very quick one, Henry. Sorry.
Just a more philosophical point. I mean, with all these studies of interactions of main effects, they look principally at the parameters, but does anybody have a clear idea what the model actually looks like when you have, say, 3 two-way interactions and no 3-way interactions? It's very difficult to actually have an idea of what the level sets of the function output looks like in this case. I mean, what I'm saying is the interpretation of the output when you have, and why should you have 3 two-way interactions and not have a 3-way interaction? I mean, surely if I'm talking to you and you're talking to Angela and you're talking to me, we all go to the pub together, 3 of us, right? So in some way you should be imputing higher order interactions once you know two-way interactions.
That's sort of like what Jeff is saying about going to the two-factor interactions when you know what something about the main effects, and that's the next stage. Yeah.
Okay, well, we must call a halt to discussion, but it'd be great to continue at the end of this session. Thank you, Angela.